Okay, we've got a very important problem here, very much like an AP problem. Chapter 12, Review 1, we have a table with derivatives. We've got derivatives and the function itself evaluated between 1, 2, and 3. Function h and all four derivatives are increasing on this interval, we are being told. So definitely want to work this through. Let's take a look at part A. It says write the first degree Taylor polynomial for h about x equals 2. And when they say about x equals 2, they mean centered at x equals 2. We're going to use that Taylor polynomial to approximate h of 1.9. And we want to know if this approximation is greater than or less than the actual value, and explain your reasoning. Well, for part A, notice what I'm going to do. I'm going to write P for polynomial, 1 for a degree of 1, and I'm centered at 2. That means I'll have h of 2 plus derivative of h of 2 times x minus 2. And without too much work here, you can see h of 2 is 80, and h prime of 2 is 128. And hey, look at that. Without hardly any work at all, you have your first degree Taylor polynomial. Now, of course, what they're going to ask is, could we get an estimate for h of 1.9? H of 1.9 is about what you would get plugging 1.9 into your polynomial. Obviously, this is just an estimate, but this is where we can take the calculator out and type in 80 plus 128. Our x value is 1.9. And working this thing out, you can see pretty quickly you'll get 67.2. So that is your estimate. Here is your first degree Taylor polynomial. There is that third part of the problem, and they're saying, well, are you too big of an estimate or too small? And this is where we're going to go back and realize this question is review. It might not seem like it, but a first degree Taylor polynomial is a tangent line to the curve. Very important for us to realize we have a tangent line. So what you have is your actual curve. You're getting a tangent line drawn at the point 2, 80. I'm getting that right here. That's my point of tangency. You might wonder how we can know if a tangent line estimate is going to be an underestimate or an overestimate. The answer that we had last semester was we wanted to look at the second derivative. You can see that our second derivative at x equals 2 is actually positive. We can also see that it's positive everywhere and all the derivatives are increasing. So that means you're concave up. By the way, I kind of drew the curve assuming that. I shouldn't have drawn the concavity until I knew that. But regardless, if you have a concave up curve, your tangent line will lie underneath. You'll have an underestimate. So they want you to explain your reasoning. So you can say that this estimate, P of 1.9, must be less than the actual true value, because P1 of x, that first degree polynomial, is the tangent line drawn to the function, so it's drawn to f of x, or h of x, pardon me, at the point 2, 80, and h double prime of x is greater than 0 on the interval. That's what you're really looking to communicate. So some great review that we really do need to continue to pick up. So let's take a look at part B, which is amazingly similar, but they're asking us to do something with a third degree polynomial. And how is that any different? Well, you could say, well, your third degree, here's for part B, your third degree Taylor polynomial, well, we're centered at 2, so we'll have h of 2 plus h prime of 2 times x minus 2 to the first all over 1 factorial plus h double prime of 2 times x minus 2 to the second all over 2 factorial plus, well, now we can stop. Here's your third degree derivative of the third derivative, x minus 2 to the third all over 3 factorial. Let's just go ahead and clean this up. Point of interest, you're going to see that you've got that first degree polynomial already built in. That's that tangent line we were just looking at. And h double prime of 2, well, we saw that's 488 all over 3 from the table up there. And then as we take a look at the third degree, almost looks the same. It's actually 448 all over 3. And by the way, 2 factorial is just a 2, and 3 factorial is actually just a 6. Now, we might as well clean this up. We should. And, as you just divide and clean this up just a little bit, 488 all over 3, you're going to take half of that. That's going to be 244 all over 3 times x minus 2 squared here. And here, if we're going to take 1/6 of 448 all over 3, you'll get 224 all over 9. What I just did is I took half of the top, knowing that I'd still have a 3 down below. You can confirm that by writing it out step by step if you'd like. But there's your third degree Taylor polynomial. Now, what are we asked to do? Plain and simple for part B, they just want you to actually evaluate, approximate what's happening when you plug in a 1.9. You want to get an estimate. So if we were to, just plug that in, we'd see that h of 1.9 would be approximately equal to this third degree. All I'm going to do is I'll get the calculator out to get some assistance here. So we can say I'm going to bring this back. Here's second enter. Here's your 80 plus 128 times 1.9 minus 2. Then we'll say plus, well, you can get a fraction up here and get 244, all over 3. And then up in here, we'll say 1.9 minus 2, but we're going to square it. And then finally, you can see if we just slide this over, we've got 224 all over 9. So we'll go alpha y equals, get a fraction going. 224, bring that down here to 9. And then what? Well, we'll say it's 1.9 minus a 2, and we're bumping it up to a 3. When you hit enter, you're going to see that you get roughly about 67.988. And remember, in AP rounding, we'll just go to 3 decimal places. And so that, honestly, is that second part. They wanted you to first get the polynomial. Then they want you to use that so that you can, get a good estimate. Okay, so we just got an estimate. We got about 67.9888. Here's the bigger question. Just how accurate are we? Part C, it says use the Lagrange error bound to show that the third degree Taylor polynomial, which you just used, about x equals 2, has error less than 3 times 10 to the negative 4th. You can think, how in the world do we do that? Well, here's how. We were working with a third degree polynomial. You might remember from the video on 12.11. It's very much looking like we're using the same expansion that we've been using for all along here for the Maclaurin and Taylor series. But what's going to happen is for the Lagrange error bound, we're going to go an extra derivative, go to an extra power. Notice what is not happening. You're not plugging in where you're centered. You're plugging in a z. And z is going to be between where you are centered and what you are estimating. Z must be bigger than 1.9 and less than 2. So this is very, very important. We don't know what z is. We just know that z must be somewhere between those. And right now, I think the very, very, very big question that we're wrestling with is we don't seem to have a fourth derivative evaluated for something in between 1.9 and 2. If you look up here, our fourth derivative, really want to make a point of this. Our fourth derivative, we have a value at 2, we have a value at 1, we have a value at 3 for our fourth derivative. We don't have something between 1.9 and 2. And this gets to be rather, tough. You'd say, look, your error must be less than this. Your error that you just used in your estimate has to be less than this fourth derivative evaluated at some z. I'm going to plug in a 1.9 minus 2 to the fourth because, I'm plugging in this 1.9 right now for my estimate. And down here, you've got your 4 factorial. But we look at this and we'd say, well, I don't know what that fourth derivative value is. But remember, we're trying to deal with a worst case scenario. We're trying to say what would make this error as large as possible so we could say we can't do any worse than this. Please understand that your derivatives are increasing. So 1.9, you'd say, I don't know what my derivative of the fourth derivative of h is at 1.9. I do know what it is at 2, but I know that these values keep getting larger and larger and larger. So what I can do is plain and simply this. I'm going to say, look, worst case scenario, I'm going to assume that this can only get as large as 584 all over 9. It's actually less than that. It truly is less than that. But now what do? You just work this thing out, and it's going to be your error bound. So we'll take out our calculator real quickly. I'm going to go ahead and get alpha y equals. I'll get a 584 all over 9. And then we can say we're going to multiply that by 1.9 minus 2. And that's all the way up to the fourth power, I believe. Don't forget, you're still going to have to divide by a 4 factorial. We can do that in a moment. When you divide by 4 factorial, by the way, 4 factorial, if you think about it, that's 24. And if you get that, you can see that we're going to have an error of 2.7037 times 10 to the negative fourth. So we'll be at about 2.7037 times 10 to the negative fourth. That's the maximum error you can have, but that's less than 3 times 10 to the negative fourth. You've just shown that your error is less than what has been asked for. It's important to comment that h of 4 of x is increasing. Again, that's why we deal with this worst case scenario. We'd like for our derivative there to be as large as possible.